Hello dear students of plus 1 medical and non-medical stream, respected teachers. So in this video of rotational motion I am going to discuss angular momentum of a single particle, angular momentum of rigid body, as well as law of conservation of angular momentum and its applications. So let us start. Angular momentum. The moment of linear momentum is called angular momentum, just like moment of force is called torque. Moment of linear momentum is called angular momentum. So it is also a vector quantity. To find expression for angular momentum of a single particle, let a particle P at location R vector, let small p vector is the linear momentum acting upon the particle. Theta is the angle between linear momentum P and direction of position vector R. Let ON be the perpendicular on the line of action of linear momentum as shown in figure. So xy is the plane of the particle and z axis is the axis of rotation as shown in figure. Then angular momentum L is given by P, that is product of magnitude of linear momentum and perpendicular distance of the direction of linear momentum from the axis of rotation. So P into ON, and from this right angle triangle again, ON upon OP, that is perpendicular over hypotenuse, is equal to sin theta, or ON is equal to R sin theta because OP is equal to R. Therefore L is equal to RP sin theta, or L is equal to R cross P. So angular momentum is the cross product of R vector and linear momentum vector P. So special cases, when theta is equal to 0 degree or 180 degree, L will be 0. So we cannot open or close the door by applying force parallel to the plane of the door, because torque is 0 as well as angular momentum is also 0. Theta is 9 degree, angular momentum is maximum. So it is very easy to open or close the door by applying force at an angle of 90 degree to the outer edge of the door, because both torque and angular momentum are maximum. When R is 0, angular momentum is 0, torque is also 0, we have proved. So to increase angular momentum, R should be as large as possible. Just we can take example of hand pump. The handle of the hand pump is quite long to increase torque and hence angular momentum, so that it is easy to run the hand pump. And angular momentum vector quantity and direction is given by right-handed screw rule or right-handed thumb rule. So for right-handed thumb rule, direction of L is given by R cross P, the vector product of R vector and P vector, so it will be along Z axis. Then angular momentum of rigid body. Again, suppose a rigid body having masses m1, m2, mn, r1, r2 are in normal distance, just like in case of torque we have done. Let p1, p2, pn be the linear momenta acting upon individual particles respectively x by the axis of rotation. Then angular momentum of mass m1 is given by L1 is equal to r1 p1 sin 90, because the path will be circular. So angle between P and R will be 90 degree. So R1 P1 sin 90 or sin 90 is 1, R will be R1 P1. But P1 is equal to M1 V1. But V1 is equal to R1 omega, because we are now converting linear motion into rotatory motion. So relation between linear velocity and angular velocity is V is equal to R omega. So it will be L1 is equal to M1 R1 square omega. So L1 is equal to M1 R1 square omega. Similarly, L2 is equal to M2 R2 square omega, and so on. Ln will be equal to Mn Rn square omega. So this gives angular momentum of various n particles. Then total angular momentum will be equal to L is equal to L1 plus L2 plus 1 Ln, because we simply add all the angular individual momenta because they are acting along that axis. Direction of angular momentum is along that axis, so they are added simply. So it will be L is equal to M1 R1 square plus M2 R2 square plus 1 Mn Rn square into omega. Omega is common. And again L is equal to I omega, where I is equal to summation M R square, or M1 R1 square plus M2 R2 square plus so on plus Mn Rn square is called moment of inertia of a rigid body, and if omega is equal to 1 unit, L is equal to I. So from this equation we can also define moment of inertia is equal to angular momentum required to produce unit angular velocity. So there are so many definitions of moment of inertia. So moment of inertia in case of angular momentum is equal to angular momentum when required to produce unit angular velocity. So we can find relation between torque and angular momentum also. So we has proved L is equal to I omega in vector form. Differentiating both sides with respect to t, we get dl by dt is equal to I d omega by dt. But d omega by dt is alpha, angular acceleration, rate of change of angular velocity is called angular acceleration. So dl by dt is equal to I alpha, but I alpha is nothing but torque. That's relation we derived in the previous video. So tau is equal to dl by dt. So which is known as second law of rotatory motion. Just like second law of translatory motion, F is equal to dp by dt. So tau is equal to dl by dt. Now if no external torque is acting on a system, dl by dt will be 0 or L is equal to constant. It means if no external torque acts on the system, angular momentum is constant, and this is nothing but law of conservation of angular momentum. We have law of conservation of linear momentum in translatory motion also. Here we have law of conservation of angular momentum. If no external torque is acting, angular momentum is constant. Prove, you may be asked, state and prove law of conservation of angular momentum. So to prove law of conservation of angular momentum, as tau is equal to dl by dt. If no external torque is acting, tau is 0, dl by dt is 0, therefore L is equal to constant. L means I omega, it means I omega is also constant. In other words, I1 omega 1 is equal to I2 omega 2. Or if I1 is greater than I2, omega 1 will be less than omega 2. Because product remains same, and vice versa. It means when moment of inertia increases, angular velocity decreases, and vice versa. And this principle of law of conservation of angular momentum is used by diver, by ballet dancer, by circus acrobats. So while diving, the diver holds his legs and arms when on the top in order to decrease moment of inertia and hence to increase angular velocity, so that he enters into water smoothly to get maximum points. So this principle is very, very important, used by divers, circus acrobats, ballet dancer. Or you can take simple example. Suppose you are standing on a rotating table which is frictionless, capable of rotation, and take two weights, equal weights in your hands. Then table is at rest now. Bring your weights near your chest. You will see the table starts rotating, because by bringing these weights near your chest, moment of inertia decreases and angular velocity increases. This is how angular velocity and moment of inertia are related to each other. All the best, be happy, stay tuned. Stational motion बहुत सौखा चैप्टर है, तो थोड़ा इन्हें easy लगू, चक दोगे फटे, no problem. Be happy.